Welcome again, everyone who is watching this lecture. Today we'll be discussing cross-section properties. In particular, we have centroids and inertia. Now, these cross-sectional properties like centroids and inertia will be very useful in future or higher engineering subjects such as mechanics of deformable bodies, wherein you are to determine stresses, and in higher subjects like steel design or any design subjects in engineering, the properties of centroids and inertia are very much in use. Now, the objective of this lecture is to first for you to be able to locate the centroid of a cross-section and to calculate the moment of inertia of a cross-section. Now, to do this, I will have a discussion of the concepts, theories, and information to attain the objectives. There will be an open forum or student evaluation, but in the case this is an online lecture, you can comment your questions on the comment section, and then I'll try my best to reply on your questions, and there will be problem solving to optimize the lecture. And there will also be problem solving to optimize the lectures that was discussed. So what we will be needing are calculators, notes and pen, and references. So let's start off. So when an area is bounded by a curve, as you can see in this figure, and let me just so when an area is bounded by a curve, the best solution to get the area under this curve is by using integration. This is for complex cross-sections, but in common shapes, there are standard formulas. For example, the area of a rectangle, the area of a triangle. There's an equation for you to get the area of that particular shape, or if it's a composite shape, we just simply get the total area of that of the common shapes constituting the cross-section. But for a curve, it is ideal to use integration. Again, if you have a cross-section, for example, a T-shaped cross-section that is composed of rectangular cross-sections, then you can simply just use or add up the areas of a rectangle. Later on, you will be dealing with composite shapes. But for now, we just have to use integration. Now, in integration, we use vertical strip having a height equal to y and a width of dx. Or we can also use the horizontal strip. So never mind this typo. This should be horizontal strip. So the horizontal strip has a width equals to x and the height equals to dy. Now, to obtain the area, we use integration. So it's a process of adding up the differential areas obtained from getting the area of this differential rectangle. So the total area of the differential rectangle is giving you the area of the area bounded by the curve, because you're adding up the very, very small rectangles until you get the sum of all the small rectangles, that is the area. Now, it's in a similar manner the same principle applies when we're using a horizontal strip, because this time, instead of using a vertical strip, we're using a horizontal strip, and we add up all the horizontal strips. Now, the process of adding those very, very small strips is integration. So it's either you use a vertical strip, that is integral of y dx, this is the area of your differential rectangle, and the integral of x dy, this is the area of your differential rectangle. If you integrate this differential element, then you can have the area. So in the process of getting the centroid, we will be using integration. So the first moment of area will be discussed in this part. So the first moment of area is something like this. Recall that in forces, the force has a tendency to rotate an object. So that is a moment. So moment is a factor of the force vector and the distance. So in scalar analysis, moment is simply defined as force times distance. Now in area, there is a term of what we call movement of area, wherein the moment of area is simply the area times distance from a reference axis. Now, considering differential area dA as shown in this figure, it has a moment area about the y-axis, which is dA times x, and it also has a moment area that is dA times 1, and we call that as first moment of area. Now, this first moment of area appears in several branches of physical science. And the most common notation that's used to call this one, to annotate this one is Q. So for first moment of area, we use the simple Q. Now, if we get the moment area of this differential area about x, and we get all the first moment area of all the differential areas, then we get the total moment area of the whole shape in this case. So in the process of integrating this differential area, we get to have the first moment area of the whole cross section. Now this first moment area will then be used to get the centroid, or to locate the centroid of the cross section. Now for the first moment area about the y-axis, it can be said that this is simply the integration of dA times x, or in a more convenient way of writing, that's x dA. So standard way of writing it should be x dA. That is the moment area of this whole cross section about y-axis, or simply q sub y. On the other hand, if you want to get the first moment area about the x-axis, that's simply the integration of y dA, and that is qx, or the moment of area about x. So again, it's similar to how a force tends to rotate a certain point. So this time, how an area is being rotated about a certain axis. So for you to easily understand or recall this one, qy refers to rotation of an area about y-axis. That's qy. And qx is the rotation of area about x-axis. So if we perform integration, I said that a while ago that this is the area, the moment area of the cross section. But as you can see here, the term y dA is the area, and the lever arm, or the distance from the reference axis, is measured from the centroid of that differential area to the reference axis. So if you add all this differential area, in which the distance is measured from its centroid to the reference axis, and similarly, if you integrate that, you will have the moment area of the whole shape that is measured from its centroid, which is x bar. So it's the same principle with the Varinon's theorem on the resultant for coplanar force system. So if the resultant of the moment area of this differential area, resultant, or the sum of all the moments of this dA about y-axis, is equal to the area times x bar, or the moment of the area. Now this expression will allow you to solve for the value of x bar, or which is the centroid of the cross section measured from the y-axis. So if you rewrite this equation, recall that qy is equals to integral of y dA, and ax bar is on the left side of the equation. And if you bring a on the right side again, you will have this expression. Now, as you can see, the location of the centroid measured from the y-axis, or the horizontal distance of the centroid of a cross-section measured from the y-axis, is simply the first moment area divided by the area. So you will just simply integrate the YDA and then divide it with the magnitude of the area, you will have the location of the centroid. Now, in a similar manner, obtaining the value of the location of centroid from the x-axis, we'll just use the opposite. We'll just turn x into y and y into x. So that becomes now y bar is equals to the moment area of the whole cross section about x divided by the area of the cross section. So you have now x bar and y bar. So our objective, the first objective, is about getting the value of x bar and y bar. So what is the essence of having x bar and y bar? So x bar tells you the distance of tells you the location of centroid measured from the y-axis, and similarly, y bar tells you the location of centroid measured from the x-axis. Now, let me introduce you the term neutral axis. So this is the neutral axis. It is a horizontal line that passes at the centroid. So neutral axis actually divides the cross-section in which the area above the neutral axis is equal to the area below the neutral axis. So this is also a neutral axis. This time, it's a vertical neutral axis. So the neutral axis divides the area on the left and the area on the right. So meaning the area on the left of the cross-section is equal to the area on the right of the cross-section. So the property of the neutral axis is that it is the line where the centroid is located. So if you take a look at this horizontal neutral axis, this line where C is lying along the horizontal axis. Now on the vertical axis, the axis along y-axis, which is parallel to y-axis, point C is lying also on that neutral. So the neutral axis cannot be here since the centroid is somewhere here. So the neutral axis is always contains the centroid. So let's talk more about centroid. If the region is symmetric, then its centroid is located on the axis of symmetry. So take a look at this flange. This is a steel flange used in so many structural applications. When we say symmetric, if the neutral axis is located somewhere in the middle, or it's most likely to be in the middle, then you can see that the top portion is symmetric with the bottom portion. If you have a neutral axis, a vertical neutral axis, you can see that the left portion is mirrored to the right portion, and that is what we call symmetry. Now we have here a timber. So a rectangular cross-section is symmetric on both horizontal and vertical axis. So the neutral axis along x makes the top portion and the bottom portion symmetric or in a mirror manner. So it's the same when you do a vertical neutral axis, because the left portion is mirrored to the right one. So that's what we call symmetry. Now in cases where the object is symmetric, centroid always lie on the axis of symmetry. It's always on the symmetry, because obviously it will not tend, the neutral axis will not tend to be on the upper portion, because it will not give equal area on the upper and lower portion. Because centroid tells you where should I locate the neutral axis such that the upper portion and the lower portions are equal in terms of area. So most definitely, for a rectangle, the neutral axis should lie on the mid-height. It's because it will give you equal area on top and the bottom. For a triangle, for example, obviously, the neutral axis should not lie on half of the height of the triangle. Basically because the lower portion will have more area than the upper portion. So, again, this is the equation that we use in locating the centroid. But the common engineering shapes, the common shapes in engineering, try to look at the buildings. The common shapes used in beams are rectangulars, rectangular perfection. In some steel structures, you will see something like this one, flange. So they're not very complicated cross-section. In fact, they're just made up of rectangular cross-sections. Now, to simplify the calculation of, or locating the calculation in locating the centroid, we use the principle of composite shape, composite shape method, because we are trying to avoid the use of integration. Recall that in your integral subject, this has been part of the application. Locating the centroid is already incorporated in integral calculus. But this time, since we're dealing with composite shapes or shapes which may not be rectangular, not triangular, but is made up of common, like this one, like this plant. This may not be rectangle, this may not be triangle, this may not be a square, but it is a composition of common shape. So it's a composite section composed of common shape. Now, when we are talking about common shapes, then we can evade the process of using integration because we'll be using the composite shape method. Now, in the composite shape method, we have to get the first moment of area of the whole composite shape by adding up the moment area of the common shape composing it. Okay? So this is again what they call the method of composite area. Now, in method of composite area, it is important for us to get to understand how to get the moment area of the common shapes constituting the composite shape. So more commonly, like what I've said, the composite shapes we use in engineering, particularly in civil engineering, are just cross sections which are very simple. So very rare are using triangular cross sections. Most of them are in rectangular cross sections. However, I have specified here the location of centroid and the area of the common shapes that might constitute their composite shape. So you have here the location of centroid of the triangle, which is 1/3 of A plus B, and the location of centroid measured from the x-axis, that is 1/3 of h, and the area is 1/2 base times height. For quarter circle, the location of x bar and y bar is also presented here, and the area. So other common shapes we have here are spandrel and a portion of parabola. But this time, I think not most of the cross-section uses a portion of parabola. But if, in my personal opinion, if there is a parabola, it's more convenient to use integration. But if you have, if you do not, you cannot recall the location of centroid, then there's always the process of integration wherein you can still obtain the location of centroid. Now, how is the centroid of the common shapes important in the composite shape area? Now, later on we will apply this one. So now let's have just a little practice on how to get the centroid using integration. But before we start with actual calculation, let's have first the procedure. Now, the first thing we do, recall in the integral calculus, we have to select an appropriate coordinate system. So the most commonly used coordinate system is the rectangular coordinate system in getting the centroid. So, example, we use the rectangular coordinate system. So we will select a differential element. So it's either you use a vertical differential element or differential vertical strip or a horizontal strip. So now these are differential elements because this is a very, very small strip of rectangle. So it's either vertical or horizontal. Now have to define the differential width. For a vertical strip, you use dx. For a horizontal strip, you use dy. Now, it is important for us to properly address the moment arms. So X curl or Y curl represents the centroid of the differential strip measured from the desired axis. So X curl is used if the desired first moment is you want to measure it from the y-axis, then you use X curl. If you want to locate the centroid from X, you use Y curl. So similarly for this one. Now we set the limits of the integral. Definitely, if you want to get the centroid measured from the centroid of the cross section bound by this curve, then the limit should be from this point up to this point. So you have to set the limit of your integral. If you set the limit up to this point only, definitely you will only get the centroid of the cross section in which the area is bounded from this point to this point only. So if you want to get the centroid of this whole curve, then I want to locate the centroid of this whole curve, then your integration should contain this curve. Now let's apply the equation. So x bar is equals to integral of x curl dA integral of dA. So this integral dA is simply the area, the total area, and this is the moment of area of the differential rectangle. So integrated to get the first moment area of the whole block. So the same equation goes for y bar. Whereas in the composite area, observe that this cross section might be complicated, but it is simply an assembly of common shapes. As you can see, you have here rectangles, semicircle, triangles, and another rectangle. So if the cross section can be constructed using common shapes, then it's practical to use method of composite area to eliminate the process of integration. Now, the first thing you do is to divide the section into finite number of common shapes. So divide this into regions, wherein those region is a common shape, like rectangle or triangle. Now, if a composite body has a hole or a geometric region, it means it has no material, then consider the composite body without the hole, or consider the hole as an additional composite part having a negative area. So in this case, you can consider a whole rectangle provided that you have to subtract the semicircle. Now you will appreciate this one once we proceed with the application. So we have to establish the coordinate expressed as x curl and y curl. Now in this case, y is measured from here and x is measured from here. But I still recommend you measure the centroid, or you establish y-axis on the leftmost portion, on the leftmost side of your cross-section, and the x-axis on the bottommost part of your cross-section, so that everything will be measured from the leftmost side and everything will be measured from the bottom. Now, for solving for using method of composite area, I recommend for a more organized solution, we use the table wherein it contains the region, area, x curl, y curl, and the first moment of area measured from about y-axis, and the first moment of area measured from the x-axis. Again, you can only get the centroid if you have the moment area divided by the total area. So if you have this is more of a procedural solution. So once you get the moment area x bar, and the sum of it, you will simply divide qy with the area, and then you will get x bar. If you divide qy with the total area, you will get y bar. So this is a very easy solution, but it is only applicable if your composite structure or composite shape is made up of common shape. So let's locate the centroid of this given shape using integration, because the cross section is not commonly made of a common shape, then the best solution is using integration. Okay, so the first thing we do, so the first thing we do, it is suitable to use a coordinate system that is a rectangular coordinate system that is shown in the figure, because we will be using a differential rectangle having a width dx. So this time I'm using a vertical strip. Now the differential element, we have here the rectangle. The height is equal to y and the width is equal to x. Now if our intention is to locate the centroid measured from the y-axis, we use x. And for locating the centroid measured from the x-axis, we use y. So solving the location of centroid using the equation, so the integral of y curl dA over integral of dA will allow you to solve the centroid measured from the x-axis. So take note that the first moment of area of this differential rectangle is area times its lever arm. So the lever arm is measured from the centroid to the desired axis. So the desired axis where we want to measure the centroid is the x-axis. So take note that the first moment of area is a factor of area and the lever arm from which it is measured, from which the lever arm is measured from the centroid to the desired axis. Now, if the centroid of the rectangle falls on its mid-height, which is y over 2, then you will have y dx being the area. So you have the area of the rectangle having a height y and the width dx, and the lever arm is y over 2. So you have this expression. Now, the reason why I have just put dx on the rightmost portion of the expression is because it's the standard way of writing your integral expression. But you can write it first as y dx times y over 2, and then eventually you can rewrite it for it to be more organized when you have to write it this way. So this is the area, and this is the lever arm y over 2. And that is divided by the total area, or the integral of y dx. Again, y dx is the area of the differential rectangle. If you proceed with the integration, you will get the area bounded by curve. So after having your equation, do not forget the limit. So we want to get the area from x equals to 0 to y is equals to 0 to y is equals to 1. Now, about x-axis, that is x equals to 0 and x is equals to 1. Now, your term is dx, therefore your limit should be along x. So that's from x equals to 0, x equals to 1. So 0 to 1. Now, this is a very simple expression. However, you can press this using your calculator, but if you think you're more convenient in using the manual simplification of this expression, then you can do that. So if you press it in your calculator, you will have the value of y. But take note that y is equals to x squared. So you cannot proceed yet with the integration since you have here dx. So everything has to be expressed in terms of x. So rewriting this equation wherein y is equals to square root of x, or y is equals to x squared. So y is equals to x squared. So you have this equation. So pressing that to your calculator gives you a value of y bar equals to 0.3. Now, the same manner can be used to attain the location of a centroid measured from the y-axis. This time we'll be using the first moment of area about the y-axis. That is dA, is the area of your differential strip, and the lever arm is x curl or equals to x1. So since dx is very, very, very small, you don't have to take into consideration the the mid length of the width, because this is very, very small. As compared to the value of y on the previous calculation, we divide it with 2 because it is not a differential element. I mean, it's not differential height compared to dx, which is a differential width. So you can simply express it as x squared or x. So dA, the differential area, is the same, y dx, multiplied by x being the left measured from the desired axis where we wanted to put the centroid. Now that is divided by area. This is the same from the previous equation. So just make sure that you're using dx, so you have to express everything in terms of x. So as long as you have y here, you have to express this in terms of x. So y is equals to x squared. You replace everything. After replacing y is equals to x squared, everything now is in x. So you can proceed with solving for the x bar. You can use the manual, the hand calculation of integration. You can use calculator. Either way works great. So it's up to you. But for me, if you have your calculation, then why not? So you can use your calculator or easier calculation that its x bar is equals to 0.75. Okay. So let's draw the centroid. So we have determined x bar equals to 0.75. So that means it's 0.75 meters away from the y-axis, and y bar is 0.3 meters. So that is 0.3 meters above the x-axis. Take note that it is sign sensitive. So if the measurement is to the right, then you have to take it as positive. But if your measurement is to the left, that is negative. So in the event, I'm really saying that you have to take into consideration that the reference axis should be on the leftmost portion, and the x-axis should be at the bottom portion, because we want to avoid the negative values of lever arm. That's how you get how you locate the centroid using integration. Now let's have the second example. But this time, as you can see, this is a complex shape, but it can be made up of common shapes like triangles, rectangles, and quarter circle. So instead of using integration, it is more practical to use the method of composite shape. So in the method of composite shape, or composite shape method, first thing we do is we divide everything into regions. Now take a look at the figure. I have divided this shape into region 1, which is square, 2 as a rectangle, region 3 as a rectangle. But take a look that there is a hollow portion, quarter circle, that is hollow. So I will consider this area, but this will be negative in the analysis later on. So in method of composite area, again, it is important for you to understand where is the centroid of each common shape that constitutes the full composite section. So if you do not know the centroid of a triangle, then this composite shape method will not be appropriate for you. But the essence of using this one is that you have to know where is the centroid of the common shapes, because the moment area is simply the area times the lever arm of the common shape. So area times lever arm of 1 measured from 1, area 2, lever arm of 2, area 3, lever arm of 3. So if you do not know the lever arm, the location of the centroid, then it will be hard for you to get the area. And not just hard, but it will be erroneous. So let's have here the reference axis. So the reference axis are y. It is placed on the leftmost side of the shape, and x at the bottom. So all of the lever arm will be measured positive, in a positive sense.
So let us now locate the center. Again, it is very simple. The moment area of 1 plus the moment area of 2 plus the moment area of 3 minus the moment area of 4 is the moment area of the whole shape. So in the method of composite section, we'll just add up all the moment area and then divide it with the total area of the whole. Again, locating the centroid of each common shape is very important. Now I tabulated everyone. Let's start with region 1. The area of 1 is 2.25 and its centroid falls on 0.75 measured from the y-axis. Rectangle, the square has a width of 1.5 and the centroid of the rectangle is on the mid-width of this 1.5. So this is 0.7. This is your x bar. Now the y bar is measured from the x-axis. Now, the centroid of this square is located mid-height of this 1.5. So the mid-height of 1.5 is 0.75 relative to this axis. But relative to x, that is not 0.7. It is 2.25. Because 0.75 from here to this line and 1.5 to x. So that's 0.75 plus 1.5. You have 2.20. The fourth and fifth column will just be the product of area times x bar, x curl, and the last column is simply the product of area y curl, that is 5.66. Now we will do the same process for the next regions. So proceed now with the second region 2. This is a triangle having a base of 1.5 and a height of 1.5. You have to get the area of the triangle, that is 1/2 base times height, and that's equal to 1.30. You locate now the centroid of the centroid of region 2. So since this is a triangle, centroid measured from this axis is 1/3 of the base. So the 1/3 of 1.5 is 0.5. Take note that we are not measuring it from this side. We are measuring it from the y-axis. Everything has to be measured from the datum or from the reference axis. So x square 2 is 1. Tells you the location of the centroid of triangle 2. So that is because 0.5 plus 1.5 gives a value. Y curl 2. So the 1/3 of the height is 0.5 measured from this side, but again we are measuring it from the x-axis, so that is 1.5 plus 0.5. Now complete column 4 and column 5. That is area times x squared 2.20. And the same area times x squared 2.20. Now the region 3 is much more easier. This is a rectangle. The area is 1.5 by 3. So that is 4.5. The location of centroid measured from the x-axis, measured from the y-axis or x curl, that is equal to 1.5. So this is 3. So the centroid falls on the mid-width. So if this is 1.5, this is 3, this is definitely 1.5. Now for the height, you have a height of 1.5. Definitely, the centroid falls in the mid-height of the rectangle, that is 0.0. X, measured from x, that is 0.0. And you can get ax curl and ay curl by simply multiplying area x curl and area y curl. So you have now regions 1 to 8. Now let's make a highlight on the region 4. As you can see, this region 4 is a hollow portion. So this has to be taken as a negative area. So area of this quarter circle is negative 1.77. This is simply 1/4 of the area of the whole circle having a radius of 1 point. Now x curl and y curl can be obtained from the equation given on the previous slides. As you can see here, let's go back to that. This is the location of centroid of a quarter circle. There are also values of the location of centroid for a semicircle, and most definitely for a circle, it falls on the center of the circle. So for a quarter circle, that's simply 4r over 3 pi for x bar, and for y bar, it's also the same 4r over 3. So let's use 4r over 3. So if you press on your calculator 4r over 3, using r as 1.5, you will have 0.64. Since it's the same equation with y curl, you have to do this one. So if you proceed with the calculation of ax curl and ay curl, you will have a negative value because the area is taken as a negative value. So that's negative 1.13 and negative 1. So upon completing this one, it's now easy for us to locate the center because you just simply have to get the summation of ax curl, or the moment area of regions 1, 2, 3, 4 about y-axis. That is the total moment area, or QY, 9.56. In the same manner, you can solve for the total moment area about x-axis, that is summation of ay curl, 9.56. If you want to locate the centroid, this is very procedural. You will simply divide QY with the total area, that is 6.11. Again, the total area is simply the summation of this. So x curl is equals to, the x bar, or the location of centroid measured from the y-axis. You simply divide the summation of ax curl, which is qy plus 1, divided by 6.11. So if you want to locate y bar, or the location of centroid measured from the x-axis, you will simply divide qx, or summation of ay curl, divided by area total. Substitute the values, you have x bar and y bar. So x bar is 1.57 inches measured from the x-axis, and y bar is 1.57 inches above x. That is how you can locate your centroid. We have attained our first objective. In the next lecture, we will continue to attain the second one. Thank you very much for watching this lecture, and I hope you learned something. If you have any questions, you can type it on the comment section. Thank you.